Morning, everyone, and welcome to this first session for Virus Bulletin. The title of the first presentation is Wild Android Collusion, presented by Jorge Blasco.
Okay, yeah, thank you. As I said, my name is in Spanish Jorge, but you can call me George or wherever you want, that it's better for you. And I come from City University in London, and I'm going to present this paper that we did with also Intel Security and Swansea University. But before that, I would like to mention where this paper comes from. So we were working for 2 years in what we call the ACID project. This is a project funded by the EPSRC in the UK. And it was a collaborative effort between City, Swansea, Intel Security as an industry partner, but also Coventry University. They were involved in this paper, but it's worth acknowledging them. So, and the goal of this project was to basically develop new methods to detect and track the possible, I would say, emerging threat of colluding applications. So, as a small introduction, I mean, all of you would probably know that, but the main security goals of Android are, well, Android has mainly 3 security goals. The first one is obviously protect the user and his data or her data. Then protect the apps that are installed on the device and the system resources that are like battery, and obviously finally protect the device itself. And in order to do so, it has many different security features. And the ones that I mentioned here are the ones that are at the device level. So you have most of the Linux-derived security features like process isolation, mandatory access control. We have also the app sandboxing. We have also the famous or maybe infamous permission systems, security APIs like encryption, credential storage, etc. And we also have the app signing, which in Android is not like used like in other platforms such as iOS, but you have it there also. And the main point that I want to make this is that all these security features are meant to avoid the threats that are caused by single applications. But what happens when applications start communicating each other? So we have many different ways of communicating, and many different things we can do while communicating. The first thing we can do is just cooperate, like 2 apps just simply exchange messages to do something that is useful for the user. So let's say you want to share your location with a WhatsApp contact, or you want to share the location on Facebook. You just tap the share button on the Google Maps app, and that creates an intent that sends the location information to another app you select. That location information goes to the internet, but it's because you wanted that. It's not that they are exchanging that information without your consent. Then we have another kind of communication, which we call permission redelegation attacks. And more general, outside the Android context, we call these kind of attacks the confused deputies attacks. And in this case, we have 2 apps, or more than 2 apps, but one of what app is developed by, I would say, a careless developer that created a component inside the app to access a sensitive resource. Let's say, for example, the camera of the device. But the problem is that that developer didn't protect that resource very well. So other apps can, imagine the developer does it on a service. The thing is that other apps, if the developer doesn't enforce other apps when requesting the access to the service to use specific permissions, other apps will be able to access a system-protected resource without actually requesting the permission. And that obviously creates risks for the users. But what happens if instead of having a careless developer and some apps exploiting that vulnerability in the application, we have 2 apps that do that on purpose? We would have something more or less like this. So imagine you have, let's say, an app that portrays itself as an audio notes app. So you could use the app to record notes, let's say, for example. And that app obviously has access to the microphone. And the user has also downloaded another app in the device, which portrays itself as a weather application. But the problem is that these 2 apps do more than they say they do. So the first app, the audio notes app, because it has access to the microphone, it also records the user conversations. And it uses any of the available communication channels in Android to send those conversations to the web application that, having access to the internet, is able to export that information outside. So depending on the communication channel used, there's no way by Android to enforce or to avoid this kind of behavior by the apps. And another problem is that the user, when downloading the applications and when applications are requesting the permissions, he doesn't know if these two apps will communicate. So he is not able, or she is not able, to take an informed decision when installing or when granting access to the different permissions for the apps. So when analyzing this problem in our project, we found that the most important or the most, let's say, key factors of app collusion are two. First, the communication channels, which I will review later, and secondly, the threats that can be enabled by the collusion attack. And what are the threats that can be enabled by colluding apps? Well, mostly the same threats that a single application could achieve. First one, the one that I showed, information theft. Very simple. One app steals information, sends it to the other application, and the other application sends it outside. But then we can have colluding app sets that could maybe try to steal money from the user, maybe by stealing his or her credentials, or also maybe by making phone calls or sending SMSs, messages. Then we could have also colluding apps that do service misuse, denial of service, but we could have also other kind of threat, or I would say other kind of attack, in which different applications synchronize themselves to actually achieve like the highest possible goal, or the highest possible gain for the malware developer. And the case we found has to do with this attack synchronization. So we know that some applications could be communicating to execute some threats, but how they can communicate? Well, there are many different communication channels on Android. The main problem of the communication channels between applications on Android is that some of them do not really need to go, let's say, or to ask for any kind of permission in Android. So if we want to use intents, two apps can communicate through intents without the user knowing. We could use also content providers for communication in Android. Content providers, well, probably you all know that, but are like small databases inside Android, and the most common content provider, I would say, is the contacts database. But if you want to use the contact database for app communication, you need to ask for permissions. We could also use external storage, but again, we would need to ask for permissions. And in some versions of Android, we could use the server preferences, which are a kind of communication channel that I will explain just in a bit. And you will see that intents and server preferences are involved, because those are the channels we analyzed when we executed or when we did our research that I'll display later. And then we could have also some hidden or covered communication channels in Android. Probably you are not aware of this, but all applications can read and modify the audio settings of an Android device without requesting any specific permissions. So if one application wants to send information to another application, what they could do is one of the applications could modulate the value of the volume setting, and the other application, while monitoring that value, could read different bytes. Obviously, this is not a high bandwidth channel, but it is something you could use, and you don't need to request any kind of permission. Obviously, again, you need to check if the user is listening to music or doing some things, because if the user is listening to music and the volume starts going up and down, it will be a kind of a strange behavior. There are also many other hidden or covered channels, and most of them are the kind of covered channels that exist in many other platforms or computer systems. So we can use enumeration of processes and sockets. We can also modulate the free space on the RAM or the storage. We could also modulate the usage of the CPU to send information to other processes. So regarding the server preferences, this is the channel we found that was being used by applications, and I want to explain it a little bit before going further. So server preferences is a kind of, it's a way of storing key value pairs on persistent storage on the device. And it's very simple to use. And it's widely used mostly to store application, as the name says, preferences. So if a developer wants to create a server preference file, he just needs to create an instance of a server preference object and call the get server preferences method from the context of the application. The developer only needs to provide two variables. The first one is the file name, where the preferences will be stored, and the second one is the mode. And this is the interesting one, because the mode of the server preferences file can be private, meaning that no other apps can access it, but it could also be word readable or word writable. And in this case, apps could access that file from, obviously, outside the sandbox without requesting any specific permission. The good news is that this reading and writing outside the sandbox only works on versions of Android that do not have easy Linux on enforcing mode. So up to date, I saw yesterday how the different versions of Android are now, and this would affect only 25% of the devices. So if we want to read a value from the shared preferences, we just called from the object, we just called get the kind of data type we want, specifying the key, and a default value in case that key is not found. If we just want to write a value into the shared preferences, we just create an editor, and it's more or less the same. Instead of calling the get, we call a put with the different data type, the key, and the value we want to store. But this is what we need to do if we want to read or write into or inside or an application. But what happens if we want to read the shared preferences files from applications, from different applications? So the only thing we need to do is we need to create a context object. We can't create a context object from any other context, and the only thing we need to provide is the package name. With that, we will only need to call, from that context object, we will need to call again the get shared preferences, specifying the file name, and in this case, word readable or word writable method. And we just need to, again, call the get, the specific data type, or put the specific data type with an editor if we want to save or store information. So knowing the communication channels, knowing the possible threats, what we did was to, develop an approach by using static analysis. What we did is we took a data set from Intel security, and we used static analysis to extract mainly the permissions used by the applications and then the communication channels. And by communication channels, I mean, as I said before, the intents, mostly broadcast intents, with also the static and dynamic broadcast receivers, and also how applications were using the shared preferences files. What we did after that is that we used Prolog. I don't know, maybe some of you don't know that. Some of you maybe studied this a long time ago. We used Prolog rules, which is a logic programming language. And we started, we first codified all the features we extracted from the apps as Prolog facts, and then we started generating some rules. Some of them, as the ones you see here, were used to codify certain actions. So for example, if an app was using the read contact permission, we would say that that app had access to sensitive information. If an app was using the send SMS permission, we would say that that app could be used to charge the user some money, and so on with all the permissions. And we also created some rules to specify how applications could collude. So, for example, you see a very simple rule here. It's that if the application 1 has access to sensitive information, if application 2 has access to the outside, and if application 1 communicates with application 2, we would have a potential collusion between application 1 and application 2. So with this, we use Prolog queries to find potentially colluding app sets, like, for example, the one you see there. We just call like colluding. This is a simplification of the actual code, but I think it's useful to see how it works. We just call colluding with package name, and it will give us all the possible applications that would be colluding with the application we provide. As I said, we use a dataset provided by Intel Security, and the last APK in that dataset was collected on February 2016. And we found many interesting things, but what we did is we focused on how applications were using shared preferences, because shared preferences are not, I would say, a standard communication channel in Android applications. No one uses shared preferences because you have many other better methods to communicate between Android applications. And we found two things. First, there were many applications that were using, most of the things we found were inside libraries that were being imported by applications. Some of them advertisement libraries, some of them other kind of libraries. And we found that there were many applications that were generating a unique device ID and were sharing that device ID through shared preferences with many other applications. This obviously implies, I would say it's a kind of collusion that would increase the privacy of the user because they can track which applications are installed on the same device. And that can be used for advertisement, targeting, and things like that. And the other thing that was interesting that we found is that there were many applications that were using a specific SDK that were storing a specific number inside different server preferences files. So we investigated further, and what we found is that all those applications were embedding what is called the MoPlus SDK. This SDK is developed and maintained by Baidu, and there was a malicious version that Trend Micro discovered in November 2015. The behavior of the malicious version was actually really interesting because the SDK, what it did is, among many other things, it also was able to create a command and control, well, a bot inside the app, instantiating in a service an HTTP server that would be able to receive commands from a command and control server. It will also allow the command and control server to request for user-sensitive information. If the app was part of the system image, it would allow the command and control server to install apps silently, and it will also allow the command and control server, we don't know exactly why, but it would allow the command and control server to write contacts on the contact database. All these things were found by Baidu, and what we found is that all the apps, including the Baidu, the MoPlus SDK, were having this strange behavior with the server preferences. What we found is that, well, before that, most of the research, or I would say maybe academic research on application collusion is based on sensitive information flows. But this is not the case of the MoPlus SDK. And what they did, basically, were the different apps embedding the MoPlus SDK were using the server preferences as a communication channel to select a leader to communicate with the command and control server. So the idea is that this SDK was embedded into many different applications with access, or with many different levels of access to the system. And the apps, we will be talking to each other to see which was the app with more access to the system. So that could be the app connecting to the command and control server and receiving the commands. So how does that work? Well, so imagine we have 3 different apps, all under Sandbox, and obviously all of them having the MoPlus SDK. The first thing all of the apps do when they execute is they do some checks, and they save a priority value on a server preferences file. The name of the server preferences files is always the package name plus a suffix, which is #shenk, okay? And how is that priority value calculated? Well, this is a method inside the Baidu SDK. It's obviously obfuscated, and basically there were many different checks. Depending on how the check went, you would have a different value added to a sum that was then saved to that server preference file. The first checks were just manifest tags, so the app, or best said, the SDK would look into the app manifest to check for different meta tags inside the manifest. It would check if the app was developed by Baidu and many other different things. And depending on those values, it would save, it would add a different priority value. Then the app would check if it was able to get into the contacts database, and in that case, it would add an additional priority value. And finally, the app would check if it was part of the system image. So the nice thing about all these checks is that the first checks give the priority value a little bump, but the last ones make the priority value grow a lot. So depending on the kind of checks that were true, the priority value would increase a lot depending on, obviously the app was inside the system image, the priority would increase a lot more than if there was just a meta tag found. And so what the apps did with this, so they saved, again, the same before slide, they saved the priority value into a server preference file. And after that, what they did is all the apps, including the MoPlus SDK, would read all the other preference files. And only the service of the app with the highest priority value would be launching the service, including the connection to the command and control server. So in this way, the apps were able to, let's say, optimize their attack into using the app that has most access to the system resources. So this is just how the apps were iterating to check the server preference file to look for the highest priority value, and then an intent would be created, and lastly, the intent could be launched. And the interesting thing here is that all the previous intents that call that service could be canceled because we're going to, well, the malware developers, or let's say the malicious developers that injected that code into the MoPlus SDK only wanted the app with the highest access to the system to be executed. So just concluding, the first thing, how these things can be fought. First, probably it would be interesting to develop collusion detection methods at market or device level. And in order to develop this, well, we think that it would be interesting to check how apps use the different communication channels that they have. Then it would be interesting to, if Android had a system to enforce or to check how apps communicate to each other. I know that at some point Android implemented a kind of intent firewall, but it's not being used. So applications can use intents and broadcast intents freely, and the user doesn't get any kind of notification when two apps are communicating. And obviously, the third part is, it's just an obvious thing. Just be careful, or developers should be careful when they are embedding third-party libraries, because they should be knowing what they are embedding on their apps. Not only because of collusion, but because you can insert into your app many, many different malicious behaviors. As a conclusions, first, different inter-app communications introduce risk, different risks. And the problem in Android, at least right now, is that it's not possible. The user is not aware of how apps are communicating and how apps are exchanging data. And the user is, I mean, he's aware of the permissions that every of the apps has, but he's not aware of how these apps communicate and share information. We also saw that a specific kind of collusion is possible. Again, embedding third-party libraries can be dangerous, and sometimes it's dangerous. And the good news is that at the moment, we only found this kind of synchronization attacks. We didn't find any kind of sensitive information or information theft attacks using collusion. But we don't know if there could be more apps having these kind of behaviors, because we haven't been able to analyze lots and lots of different apps. And that's it. Thank you very much.